So in our polynomial kernel video in the support vector machine chapter, we have seen that if I define my kernel like this, right? So if I define my kernel between 2 points x1 comma x2 as this, right? If this is how I define my kernel, right? We showed that this is equivalent to a dot product between 2 points in 6-dimensional spaces, right? Our original data, let's say x1 and x2, our original data points are 2D data points, right? They have only 2 dimensions. x11, x12, the 2 dimensions of the point x1, and x2 has x21 and x22, 2 dimensions. So by using this simple polynomial kernel, this is a very simple quadratic kernel actually. So we have shown that this polynomial kernel would modify our data points x1 and x2 to x1 dash and x2 dash, which are now 6-dimensional points. Look at this. These are 6D points, right? Where the first dimension is 1, the second dimension is x11 square, the third dimension is x12 square, the fourth dimension is square root of 2x11, so on and so forth, right? So what have we done here? So by using this kernel, by using this kernel, we have taken points which are in 2D. Using this kernel, we converted them into 6D points, right? And the points are explicitly here, right? So our initial points are x1 and x2, which are 2D. We've converted them into x1 dash and x2 dash, which are now 6-dimensional points, right? So at the start of this video, we have also shown about the concentric circle data set, right? So we'll come back to it in a while. Okay, this is the first thing. This is the first thing in this video. We have shown that by using this simple quadratic kernel, as a way to measure similarity between 2 points, is literally equivalent to converting your 2D points to 6D points using this sort of transformation, right? Now there is another video that we have come across in the logistic regression chapter, right? In the logistic regression chapter, we had a video called non-linearly separable data and feature engineering, where we showed that if we have a data set like this, which is 2 concentric circles, look at this. This is one class of data, right? And the blue points are another class of data. If I have 2 concentric circles as feature 1 and feature 2, I perform feature transformation. And here I'm defining my new points. Given any point xi, which is defined like this, I'm creating a new point called xi dash, right? Which consists of xi1 dash and xi2 dash, where xi1 dash is nothing but the square of the first feature, and xi2 dash is nothing but the square of the second feature. So here we are transforming data from 2D to a 2D point, right? Here we are not going from 2D to 6D or 2D to 5D. Here we're going from 2D to 2D, but because this data is concentric circles, by transforming our data like this, using these quadratic terms or using this terms which are raised to power 2, right? We made the data linearly separable. So one of our students asked a very interesting question, which is, okay, so how do you connect these two concepts? Here we have a polynomial kernel, because if you notice here what are we doing? These are related concepts. There is a very interesting subtle relation between both of them. Here what are we doing? We are taking each of these. So our xi1 dash, this one, our xi1 dash is xi1 square, and our xi2 dash, the second feature, is xi2 square. So if you notice, we only have square terms here, right? Here when I have concentric circles, by performing this simple feature transformation, I'm able to make the data linearly separable. Here if you notice, our polynomial kernel also has this x11 square. It also has x12 square. If you notice, you have these features here. These are also quadratic terms of the original features if you think about them. What did we do in the feature transform that I showed you a while ago? We raised this to power 2, we raised this to power 2, which is same as this. So 2 of the 6 features that we have in xi dash, remember our xi dash is a 6-dimensional point, but two features amongst these 6 features are simply the quadratic terms. Okay, the other terms, again, you have, this is x11 raised to power 2, x12 raised to power 2. Here you have only x11, only x12, but you have this other quadratic term also, which is x11 raised to power 1 and x12 raised to power 2. This is basically a multiplication of these two terms, right? Now, think about this. So what you have here, you have these 6-dimensional features, right? Which have all these possibilities, right? You have just a constant one, you have the square terms, you have the individual terms, and you have the multiplicative term. You have all of them. These two features alone, these two features amongst all of the 6 features can separate, they can separate your data if it is concentric circles. If it is simply concentric circle data, let's assume my data set is like this, right? Let's assume my data set is like this. I have a bunch of points from one class here, right? And let's say these are all bunch of points from one class. And let's say I have another set of points which are all here. Okay. All of them here. Now here, if you notice, all these points belong to one class, all these points belong to one class. Now, the two features amongst the 6 features, these two features amongst all of the 6 features will transform. Again, this is my original data, right? This is my original 2D data. This is my original 2D data. And when I apply this kernel, when I apply this polynomial kernel or quadratic kernel to be precise, because we are only using raised to power 2 here. A general polynomial kernel will be a plus x1 transpose x2 power b. This is a general polynomial kernel, but we're using just a simple quadratic kernel here, right? So when I'm using a simple quadratic kernel, or let's call it quadratic kernel specifically, when I'm using a simple quadratic kernel, amongst the 6 features, I have these 2 features which can help me transform this data into a linearly separable data. Just 2 of those features are sufficient. So if my data was actually like this, 2 concentric circles of data, just the 2 amongst these 6 features, just these features, just these 2 features are sufficient for me to convert this data. They're sufficient enough to convert this data from convert this data in such a way that the data is linearly separable, right? So this can be converted as we have seen in this video. This data can be converted such that it becomes linearly separable, right? So this is again inherently. So what does this mean? What does this mean? Inherently, right? Inherently. So what does this mean? Inherently, by using the quadratic kernel, by using this simple quadratic kernel, right? Just by using the quadratic kernel, I can transform my data, which is concentric circle data, into linearly separable data. Extremely powerful concept, right? So kernels literally, inherently, what are they doing? They are trying to transform your data from one dimensions to other dimensions such that your data becomes linearly separable. But now your immediate question should be, here we have 6 features, not 2 features. Here we have 6 features, right? So the answer to that is, why are the 6 features useful? Now, instead of having two circles as your data, instead of having 2 concentric circles as your data, if your data was, let's say, 2 ellipses, let's assume your data was like this, okay, 2 ellipses of data. Okay, I've almost drawn a circle, but let me make it a little bit elliptical. Okay, let's assume this is one ellipse of data. Okay, this is one ellipse of data. I have another ellipse of data here, let's say. Okay, so if you think about them, this is one ellipse of data. This is another ellipse of data. These are not actually exactly circles. Okay, so if your data is 2 ellipses, not 2 concentric circles. These are 2 concentric or two ellipses, let's say. Okay, so I'm just trying to expand it here. Okay, so that it doesn't look like circles. Then what happens? Then this simple transformation of squaring these things will not work anymore. Right? The simple squaring of these 2 terms will not work. But when you take this 6-dimensional representation, right? If you look at the Wikipedia article for a quadratic function, Okay, if you have a quadratic function has the square terms, the multiplicative term, and the individual terms, and a constant. This is called a quadratic term, a quadratic equation with two variables x and y. In our case, you can think of x as x11, y as x12, the first dimension and the second dimension. And this general purpose quadratic equation in two variables is sufficient to describe all conic sections that you might have studied in your high school, in your 11th or 12th class, or in undergraduate studies. This can represent an ellipse. This is a general form of a conic section in 2D, which can represent a circle, it can represent an ellipse, it can represent a parabola, it can represent a hyperbola. Right? So the 6 terms that we have, if you notice the 6 terms, remember you have these quadratic terms, you have the multiplicative term, you have these individual terms, and a constant. This is 1. Exactly, that's what you get here. If you see this, what are you getting here? You have the quadratic term, you have these individual terms, you have a multiplicative term, and you have a constant term. So this 6-dimensional representation that we got because of using this kernel can help us separate data which might be two ellipses here. These are 2 ellipses, right? If your data is 2-dimensional ellipses like this, not just circles, remember, not just circles. For circles, just those 2 features, the x11 square and x12 square, these are sufficient if you have 2 circles. But if you have ellipses or parabolas or hyperbolas, right, then all the 6 features would be needed. So what a polynomial kernel, literally, or what a quadratic kernel, okay, what a quadratic kernel is literally doing is it is taking your 2-dimensional data, transforming into 6-dimensional data such that, this is important, such that in these 6 dimensions, you can separate data which is either 2 concentric circles or 2 ellipses or hyperbolas or parabolas. So basically any conic section in 2D. Of course, there is a 3-dimensional equivalent to this, right? If your points were not actually 2D but 3D points, right? What you get is, again, you can do, instead of quadratic, you need to have cubic stuff there. Again, you can design lots of very interesting stuff from here. So in a nutshell, the reason I'm explaining this video is because you can think of your polynomial kernel as just the kernelization form of your feature engineering part. Your feature engineering that you have done here, manually that you have done, kernels are internally doing this for you. That's the key takeaway here.